In this video we will consider the limit of the composition of two functions. We are going to look at the limit as x tends towards a of f of g of x. The limit as x tends towards a of g of x is b, and f of x is continuous at x equals b. It turns out that this limit can be got by getting f of the limit as x tends towards a of g of x, which we've already stated is b, so that this limit works out to be f of b. For example, suppose f of x is e to the power of x. Now f of x is continuous everywhere. E to the power of x is continuous everywhere. That can be proven. Let's suppose g of x is equal to sine of x. Let's suppose we want to get the limit as x tends towards 0 of f of g of x. So here's f of x, e to the power of x. We want to get f of g of x. We want to plug sine of x in for x. So we get e to the power of sine of x. So we can apply our result. We can get f of the limit as x tends towards a of g of x. Well, we want to get the limit as x tends towards 0 of g of x. Well, g of x is just sine of x, okay? So we want to evaluate this limit. So a is 0 in this example. But we want to get f of this quantity. In other words, we want to raise e to the power of this thing. Now sine of x is continuous everywhere. In particular, it's continuous at x equals 0. So the limit as x tends towards 0 of sine of x is just sine of 0. By the way, just to follow the notation of the theorem, this quantity here is just b. So sine of 0 is our b. We could write it like this, e to the power of b. And f of x is continuous everywhere. In particular, it's continuous at b. So anyway, we end up with e to the power of sine of 0. Well, that's e to the power of 0, which is 1. To prove that the limit as x tends towards a of f of g of x equals f of b, we pick some epsilon from the outset. So epsilon is any positive number, no matter how small. Can we find a delta? So we have to prove that there exists a delta greater than 0, such that whenever x is within a distance delta of a, but x is not equal to a, in other words the magnitude of x minus a is greater than 0, then the distance of f of g of x to f of b is less than the epsilon that we chose from the outset. So this is what we want to prove. We choose our epsilon, we want to prove that we can get a delta. Now we start by noting that f of x is continuous at x equals b. So that means that the limit as x tends towards b of f of x is just equal to f of b. That's what it means for the function f of x to be continuous at b. To calculate this limit, we just replace x with b. Now we are going to write this limit using the epsilon delta notation. But the epsilon that we will actually use is the epsilon that we're choosing at the outset to prove our result, this limit here. So we assume that we are given this epsilon not just for the result we're trying to prove, but also for this limit here. Because this limit exists, there must exist a delta. Now we will call this delta not delta because we're reserving delta for what we're trying to prove. We will call this delta delta 1. There exists a delta 1 greater than 0, such that whenever x is within a distance delta of b, delta 1 of b, but x is not equal to b, because x is approaching b but never reaching b, x is not equal to b. Then we find that f of x is within a distance epsilon of f of b. F of x is approaching f of b. Next, we use the fact that the limit as x tends towards a of g of x equals b. So that means if we pick any epsilon greater than 0, now this epsilon we will call epsilon 1. And we will set epsilon 1 equal to the delta 1 of the previous limit. So we can pick an epsilon 1, we can pick this delta 1 that we used. We need to pick this one actually to make this proof work. I'll put it all together at the end so it makes sense. We just have to wait till we get to the end. Anyway, we pick this epsilon 1, which is delta 1. Now for this limit here, there must exist a delta. Now this time we are using the delta for the limit that we're trying to prove. Remember, for the limit we're trying to prove, we pick an epsilon greater than 0 from the outset, and we have to show that there is a delta. We have to prove that there is such a delta. And that's the delta we're actually going to use here for this limit. But you'll see why this delta will work. Anyway, there exists delta greater than 0 such that whenever x is within delta of a, but x is not equal to a, x is approaching a but never reaches a, then g of x is within epsilon 1 of b. So the distance between g of x and b is less than epsilon 1. And we're letting epsilon 1 be delta 1. So we're free to choose anything for epsilon or epsilon 1 here, and we're choosing it to be delta 1 to make this proof work. So let's put everything together. So because this limit here exists, we can find a delta such that whenever x is within delta of a but x is not equal to a, then g of x is within delta 1 of b. Now if we go back to the first limit we did, we saw that if x is within a distance delta 1 of b, then this result is true. So we could replace x with g of x. And then f of x minus f of b would still be less than epsilon. I'm just replacing x with g of x. Now it doesn't matter if g of x is equal to b, because then f of g of x will equal f of b, and this thing here will be 0, and 0 is certainly less than epsilon. You see, g of x could equal b because there's no requirement that the magnitude of g of x minus b be greater than 0. We don't have a 0 less than this here. That's not part of the definition of the limit. The 0 appears, of course, for the delta part. So g of x could equal b, and this result will still be true. So if we replace x with g of x, we get this. But the epsilon is what we chose from the outset. Given this epsilon, we have indeed found a delta, such that whenever x is within a distance delta of a, but x is not equal to a, then f of g of x, the magnitude of f of g of x minus f of b is less than epsilon. Which proves that the limit as x tends towards a of f of g of x is indeed equal to f of b. So the epsilon was any positive number, no matter how small, chosen from the outset. We can indeed find another positive number delta.